Welcome to the Explainer. Today, we're diving into something pretty cool. A new method that takes a really powerful but really slow type of AI and makes it unbelievably fast.
Okay, so here's our game plan. We're going to start with the dilemma, figure out the exact bottleneck causing all the trouble, then look at 3 aha moments that led to a super smart solution. After that, we'll check out the mind-blowing results and talk about what it all means for the future.
All right, let's set the stage. There's this amazing class of AI models out there. They're incredibly powerful, super flexible, but, yeah, they have one massive drawback. They are painfully slow.
So, meet the models in question. Diffusion LLMs, or DLMs for short. Now, unlike your standard AI that predicts just one word at a time, these guys work more like a sculptor. They start with a totally blank slate, a block of masked text, and they refine the entire thing at once, step by step, until a masterpiece emerges. This approach makes them fantastic for really complex jobs.
But here's the catch. That whole refining process, it's an absolute beast when it comes to computation. Think about it. It's like an artist completely redrawing an entire detailed portrait from scratch over and over just to make one tiny adjustment to an eyebrow. It's just wildly inefficient. So, let's dig into that inefficiency. What's actually going on under the hood that's causing this massive slowdown? Well, it all comes down to one word: redundancy. You know, in most modern AIs, there's a really clever trick to speed things up. It's called a key value cache, or KV cache. You can basically think of it as the AI's short-term memory. It stores calculations it's already done, so it doesn't have to waste time doing the same math again and again.
But for our DLMs, that memory trick completely breaks. Why? Because of something called bidirectional attention. It just means that every single piece of the text can see and influence every other piece of the text all at the same time. The moment you make one tiny change, the entire memory, the entire cache becomes instantly stale and useless. The model has no choice but to throw it all out and start over every single time.
And this little list right here shows you just how wasteful that is. In step 1, it computes everything for every token. In step 2, it throws it all away and does the exact same thing all over again. It is a brutal, endless cycle of compute, discard, repeat. Just a massive amount of redundant, wasted effort.
Okay, but this is where the story gets really interesting. The researchers behind this new method, Elastic Cache, they didn't just see the waste. They looked closer and noticed a few really crucial patterns, which led to their big eureka moment.
Observation number 1. They realized that the blank parts of the text that are really far away from where the model is currently working, well, they barely have any influence at all. You can see it right here in this attention map. All the action, all the focus is right here in this local area. The stuff way over there, the model just isn't paying attention to it.
Second observation. They noticed that the AI's brain, its layers, don't all change at the same rate. Think of it like this. The shallow, early layers that handle basic grammar and structure, they figure things out pretty quickly and then stabilize. But the deeper layers, the ones handling abstract meaning, they keep changing, they keep refining. This chart shows that KV drift, or the amount of change, gets way bigger the deeper you go into the model.
And the third observation, this one is just so clever. They found a weird paradox. The single most important token at any moment, the one that all the other tokens are paying attention to, is also the most stable. Its own value barely changes. And that's huge, because it means you can watch that one token to get a really cheap, really reliable signal for how stable the whole system is.
So taking those 3 insights, they built a truly brilliant and adaptive solution. This is Elastic Cache. Let's see how they put all those pieces together to build a way more efficient system. So the first big idea is how it decides what to remember. On the left is the old way, a clunky, fixed block. But Elastic Cache uses a flexible, sliding window you see on the right. This window moves along with the action, making sure it always keeps the most relevant, nearby information handy. It's just a much smarter, more flexible approach, especially when the text gets longer.
And that leads to this genius 2-part strategy. First, the question of when to refresh the memory. It uses that super stable, most attended token we just talked about. It just watches that one token. If it starts to change too much, boom, it triggers a refresh. Then the question of where to refresh. It knows from the second observation that the shallow layers are stable, so why recalculate them? It doesn't. It just recomputes the deeper layers, the ones that are actually changing. It's targeted, it's efficient, it's just brilliant.
Okay, so the theory is elegant, the strategy is smart, but does it actually work in practice? Oh yeah. The results are not just impressive, they are absolutely staggering.
On a tough math reasoning test, Elasticache delivered an 8.7 times speedup, and it did this with basically zero loss in accuracy. That is a massive leap forward. But check this out. For longer pieces of text, the effect just gets more and more dramatic. It reached an incredible 45.1 times speedup. That tells you this method scales beautifully.
And this table really tells the whole story. Look at the baseline model. It's chugging along at 2.6 tokens per second. Another method gets a decent 14x speedup. But then look at Elasticache, 45x speedup, pumping out over 117 tokens per second. And the best part? Look at that accuracy column. It is identical to the original slow model. That's the dream right there. Insane speed with absolutely zero compromise on quality.
So we've seen the method, we've seen the jaw-dropping results. Let's zoom out for a second and talk about the bigger picture here. What does this all mean for the future of AI?
So let's wrap up with the key contributions because they're huge. First, this is a training-free method. You can just plug it into existing models, no expensive retraining needed. Second, it gives us these two incredibly smart adaptive policies for deciding when and where to do the work. And the result of all this, a massive reduction in the processing time that was holding these powerful DLMs back, finally making them practical for you and me to use in the real world.
Hey, and speaking of efficiency, if you enjoyed this explainer and you're getting a good vibe from understanding all this stuff works, you will absolutely love the other stuff we do over on our YouTube channel, VibeDoc. You know, we've been talking about getting rid of redundancy. Well, the only thing that should be redundant is you clicking that subscribe button. Go on, do it for science. And that leaves us with one last big question to think about. When you can make an advanced technology like this, not just a little bit faster, but over 40 times faster, without losing any quality, what does that unlock? It's more than just an engineering win. It opens the door to completely new applications, things we probably haven't even dreamed of yet. What becomes possible now that the wait is finally over?